Hi, everyone. Thanks for joining the fourth annual of the International Day, a Women in Statistics and Data Science conference with this year's theme, Thriving in Your Environment. We are recording this event and the video will be available on the Caucus for Women in Statistics YouTube channel. We kindly ask you to post your questions to the speakers in the Q&A chat. And without further ado, I am delighted to host this session, Advances in Bayesian and Spatial Method for Environmental and Public Health Research, and introduce myself as the first speaker. My name is Jian Guan, and I am a PhD candidate in biostatistics at Drexel University. And today I will be presenting a hierarchical model to account for temporal misalignment in American Community Survey explanatory variable. So for those of you who aren't familiar with American Community Survey or ACS, sorry about that. So this survey is administered by the U.S. Census Bureau every year to provide the most up-to-date information about the demographic or socioeconomic characteristic of the communities in the U.S. And unlike the census that target to cover the entire population, this survey is about 3% of the U.S. population, and then they use the data collected over a period of time. So in order to account for the fact that this is based on the fraction of the population, the census also provides the margin of error information. And there are two kinds of ACS estimate. The first one is 1-year ACS estimate. And as the name suggests, it uses the data collected over 12 months. And it is only available for the areas with a population greater than 65,000 to ensure the quality. And there is also 5-year ACS estimate, and this uses 60 months of the data, but this one is available for all areas. But there is this inherent temporal misalignment. So for example, this 5-year ACS estimate released in 2019, we use data collected from 2015 and 19. So here I'm showing how this can show different time trend depending on what kind of ACS estimate we're using. So the first column is 1-year ACS estimate, and here I'm showing two different kind of variables. The first one is the percentage of the Black population, and then the second one is the unemployment rate. And as you can see, for this first variable, this tend to be relatively stable over time, but for unemployment rate, it seems to decrease from 2010 to 2018, which makes sense based on what we know about 2008 financial crisis. But when we look at this 5-year ACS estimate, the time trend looks a bit different. And that is because, for example, this data released in 2018 would use the data collected from 2004 to 2018. So now if you look at the unemployment rate using the 5-year ACS estimate, you can see the peak is around 2013 because it is still using the data in the previous 5 years. But we have seen this multi-year ACS estimate being used more and more in the study that try to understand the social determinants of health at county level or even final level, such as a tract level. And then when they fit this model, what they actually want to know is the cross-sectional association between the socio-demographic covariates and the outcome at a time. However, if we fail to account for this temporal misalignment in the 5-year ACS estimate, we might get the biased results. So what we propose to do is first we account for this temporal misalignment while also incorporating this uncertainty information from ACS estimate that was given by the census. And we also leverage the spatial structure to borrow strengths across the regions. So here is our motivating example. We looked at frequent mental distress among adults in North Carolina at county level from 2014 to 2018. As you can see from this map getting darker, more and more percent of adults is experiencing bad mental health in North Carolina. So we decided to dive into this topic and we found some previous study analyzed its association with socio-demographic factor at this county using the ACS estimates. But again, since at the county level, some counties don't have 1-year ACS estimate due to their small population, they use a 5-year ACS estimate. But again, there is a mismatch between the response variable and explanatory variable in terms of its time, because the explanatory variable used the data collected from 2015 to 2019. With also other literature review, which shows these variables to be included on a model, and there were 3 categories. The first one was ACS estimate that were relatively stable over time, such as the percentage of the college-educated population, which labeled as demographic variable just for our convenience. And then we also had these other variables that were more fluctuating over the time, such as the unemployment rate. And then we named it as a socioeconomic variables. And then we also included the indicator to represent if the county is more rural or urban. So again, our modeling goal is to study the cross-sectional association between county level characteristic and the mental health for each year, while addressing this temporal misalignment in the multi-year ACS estimates. So this is our proposed model.
On the web for so again,
This is our proposed model where we use the latent variable instead of 1-year or 5-year ACS estimate that was given. So the way we're doing it is we get an inference about this latent variable using all this information we have from the ACS, which I would explain more in the later slide. But this would represent the true yearly trend of the county level characteristic. And then we also added the spatio-temporal random effect so that we can leverage this spatial information, but also borrow strengths from the JSON years. So for that latent variable that would give us information about the true yearly trend, we obtain using this Bayesian hierarchical model. So we assume this 1-year ACS estimate was drawn from this distribution, where its mean is a true yearly trend, the latent variable X, and then the variance is can be calculated using the margin of error information that was given by the ACS survey. And then we can apply this layer to the counties that had 1-year ACS estimate, but for all the counties in this North Carolina, we can also have another layer, now assuming that this 5-year ACS estimate was drawn from this distribution, where the mean is the 5-year average of this true late yearly trend or the latent variable. Then we have another layer for its latent variable for the characteristic that were more stable over time. We assume that this was drawn from a distribution where this mean is constant over time. But for the variables that were more fluctuating over time, we assume that this was drawn from this distribution where the mean is a sum of theta and then spatial random effect. So this theta would represent some mean over the state. Then we added the spatial random effect to account for the variation at the state level. But this theta has naturally have an interpretation in terms of the state level average. So we could use that 1-year ACS estimate at the state level to strengthen this information. So now we're assuming this 1-year state level estimate was drawn from this distribution where this mean is theta. And we compare our model to 2 different models. The first one is a base model where we just use a 5-year ACS estimate as it is given without accounting for the temporal misalignment or uncertainty information. Then we also compare ours to the measurement error model where we account for the uncertainty in the 5-year ACS estimate, but we still don't integrate the 1-year ACS estimate for the area where it is available. Here is the quick summary about the model outcome. and this is a posterior distribution of the regression coefficient depending on what model we use. So the first thing you can notice is that for the person of the Black population, when we use a base model, this had a negative association with the bad mental health, and then it was a significant. But when we account for both temporal misalignment and then this uncertainty, now we are having this positive association and insignificant. So this shows if we don't account for these two modeling consideration, we might get very different information about the association. And now I'm zooming into a specific county to see how we can get information about its true yearly trend. So here, these gray dots are the 5-year ACS estimate, and then 1-year ACS estimate, and then the orange line is 5-year ACS estimates. And then using this information, in addition to the spatio-temporal structure, our model estimated this latent variable as this blue line. And then you can also see that from this 95 credible interval, our model is also accounting for the fact that this is not just fixed. And now I'm just showing the socioeconomic variables. And as you can see, now this true yearly trend is using both information of 1 year, 5 years estimate. So you can see how this pattern is different than 5-year and then 1-year ACS estimates. So to wrap up, our proposed model accounted for the temporal misalignment in the 5-year ACS estimate, as well as accounting for the uncertainty in this estimates. And then we also used the additional information, which is 1-year ACS estimate for the areas where it was available. And by utilizing the spatio-temporal structure, we help this county that had limited information strengthen their estimates. And then through the simulation study, we were able to observe that when the values of the explanatory variable systemically increase or decrease over time, which is often the case with the socioeconomic variable, as we have seen from the unemployment rate, if you just use a 5-year ACS estimate, this tend to either over or underestimate the yearly value. So we need to be extra careful with those kind of variables. And we also did a more simulation study to show how this can benefit study of the social determinants of health. And this is more, the more detail is written in our article. So this is a link, the QR code for the article in case you are interested in, and I'll be also happy to answer any question through the Q&A chat. For now, I will introduce our next speaker, Dr. Keller from Colorado State, for next presentation.
Hi, everyone. My name is Kaylee Keller, and I'm the next speaker in this session. I'm going to be talking about a distributed lag interaction model with index modification, and it's just a flexible form for modifying distributed lag models. I want to first acknowledge that most of the work that I'm presenting here has been done by a former student of mine, Danielle, and this was also done in conjunction with my colleague, Andrew Wilson. And so this work was published earlier this year in the journal Biostatistics under an article with the same title as this talk of distributed lag interaction model with index modification. So if you have any questions that kind of pop up throughout this presentation, a lot of the answers are in that paper, but I'd also be happy to answer questions at the end. So this work is motivated by a study of births in Colorado. So we have information from about a 15-year period of births in Colorado where we have an exposure of ambient p.5 and a response of the birth weight for gestational age z-score. And we have several different covariates that we want to include in this kind of model, but we're really interested in what is the connection between ambient PM2.5 exposure and its impact on birth weight. And specifically, we're thinking about ambient PM2.5 exposure during the pregnancy period.
You're muted.
I apologize for that. I seem to be having some technical difficulties, so hopefully I won't get bumped off again. So in the context of a distributed lag model, there's several different things we can estimate. One thing we can estimate is this exposure time response function, which is shown here by this green curve. So this is like the impact of exposure at a particular time period during pregnancy on its impact on health outcomes at pregnancy or at a later time. Another thing that we can get out of this model is information about windows of susceptibility. So part of why we want to look at repeated exposures during a pregnancy period is to identify when is it during pregnancy that exposure to air We'll try one more time here. We would like to, in this work, try to identify if we can allow for heterogeneity in the exposure response relationship, so in this beta T. And the way we would like to do that is through a what we call a distributed lag interaction model, where we're allowing for heterogeneity in this exposure response relationship beta here by allowing it to vary by an additional factor, a modifier factor here. And so can we get different estimated exposure time response curves for individuals with different values of the modifier? So the modifier in this notation is represented by the M here. And one of the ways we implement this is through the use of a cross basis. So what we can do is we want to represent this beta, allowing it to vary by a modifier. First thing we can do is have a modifier basis that expands the modifier value. And so we have basis functions. So this could just be, for example, like B-splines for the modifier value with different coefficients. And those coefficients vary by time here. So the T subscript represents time, and K is for, say, for example, 3 or 4 degrees of freedom we have in that basis expansion. And then we would then expand those coefficients eta over time. So we have a second basis expansion here that is allowing those coefficients for the modifier basis to vary by time. And that is together gives us a cross basis. As kind of perhaps a simpler way to think about it is we're just allowing everything to vary across the pregnancy period, across time, as well as across the modifier value. So those are the two dimensions where we're allowing for more variation. And what we'd like to use as the modifier in this analysis was the Colorado EnviroScreen Health and Social Factors score. So the HSF score, as I'll refer to it, is an area level measure that's been developed by researchers in the state of Colorado as a way for quantifying health and social vulnerabilities using area level measures. And so in this representation, a larger value of the HSF score represents areas that are expected to be more vulnerable to potential adverse health impacts of exposures and of different kinds. And so when we want to apply this model to this data using HSF score, we were looking at this relationship between PM2.5 and birth weight across the pregnancy period. And so if we just use the standard DLM, so one that doesn't allow for modification, we get the results that are shown here in purple, where we have, identifying window susceptibility across the pregnancy period. So in this figure, there's 3 different panels representing essentially different, the first quartile, the median, and the third quartile of the HSF scores. And so within each panel, the horizontal axis is showing across the pregnancy period, across gestation, and the vertical axis is showing the change in birth weight, Z-score, that's associated with a 1 microgram per cubic meter difference in PM2.5. And so what we're seeing here is that just we'll the purple curve across these three different panels is exactly the same because it's not being allowed to vary by the HSF score. Instead, though, if we apply our distributed lag interaction model here, we can allow for that curve to vary by HSF score. So this is what's shown with the green curve here. And it's associated uncertainty. And we can see that we don't really see much of an effect of PM2.5 on birth weight here at the higher HSF scores, but we are identifying perhaps two potential windows of susceptibility at the lower scores. And so we're getting a more flexible model by allowing for this interaction, so allowing our estimated relationships to vary by this area level measure. But we would like to, oh, excuse me. Yes, we can also look at it in the other axis. So we can also look at for susceptible areas by week. So this is kind of showing that other angle of the two-dimensional space. So in this case, the horizontal axis is now the HSF score, and the panels are showing different weeks of pregnancy. And so again, for the regular DLM, which is shown here in purple, this is just a flat line because that is the same exposure time response function across all HSF levels. It's not being modified by the HSF score. Whereas for our DLIM model, shown in the green curve here, we are seeing that there are potential windows of susceptibility during week 7. So in this case, it's identifying that this is showing us that areas that have lower HSF scores during early pregnancy maybe are time periods and groups of people that are at risk of adverse impacts of PM2.5 exposure on birth weight during that period, as well as later in pregnancy. We're identifying also, again, a group. This would represent a group of census tracts that are perhaps more susceptible to air pollution exposure at that time period within pregnancy. Now, this HSF score, though, is not just a single measure. It was constructed from many different measures. And so we would like to actually see, can we identify which of these factors that go into this HSF score are most important? So rather than treating this as just an equally weighted factors going into the score, so this is, again, is all the pieces that go into the original HSF score, we would actually like to see if we can find a data-driven way to identify which of these factors are most predictive of effect modification of the PM2.5 birth weight relationship. And so to do that, we need to take our DLM-IM model and allow for additional variation. So we want to take this term where we previously had an exposure response relationship that varied by a modifier. And instead of just using a single modifier value, now allow that to be an index. And so we're taking a vector of potential modifying factors. So in this case, those 14 elements of the HSF score, and then giving them in each a weight, where those weights then sum to 1, so that we can identify, okay, which of these factors are in this data set providing evidence for effect modification of the PM2.5 birth weight relationship. And so we do this within a hierarchical Bayesian framework for this part. So we put a spike and slab prior on those weights to provide selection. So not only do we want to weight those factors differently, but also can we identify which are the factors that seem to matter and are there factors that don't matter, and can we identify them in a data-driven way. And so just to kind of summarize what some of the simulations we looked at, this is a few settings out of many, but we wanted to look at settings of equal weights, unequal weights, and sparse weights, where we had PM2.5 values for 1,000 individuals in the simulation, and compare this DLM-IM model with selection to a DLM-IM model without selection to a DLIM model with fixed equal weights. So this is really this model that's allowing us to do data-driven indices, these first two, and the third one was the first model that I talked about today. And what we saw, as we might expect, if the true weights are equal, then there's a small loss of efficiency from allowing the model to select the weights from the data. But if the truth is that their weights are unequal, then we do get improved coverage and narrower intervals by allowing for the selection of weights. And so this is coverage in terms of that exposure response relationship is getting improved. We also are able to accurately estimate the weights themselves. So for example, in different settings, this is just showing kind of a few different scenarios from that simulation. The first column is when there's equal weights. So in these panels, this black horizontal line represents what the true weight would be. And so in this case, the first column, they're all equal. And the second column, they're unequal. And in the third column, some of them are equal, and then there's a bunch that are 0. And the take home here is just that for sufficiently large signal to noise ratio, we are really able to estimate these weights quite well with our model, whether we have selection or without selection. And in the case where we have a scenario where there are a lot of variables that we're considering, but that don't actually matter. So that's a case where we have a bunch of true weights that are 0. We're seeing that this green estimate is a little bit closer to the truth. So we're doing a better job by allowing for selection in our model here. And so when we apply this to the Colorado HSS scores, we can identify, we can make plots like this where we're saying, okay, these are the different area level and demographic measures that go into the HSF score. And we can both calculate what their estimated weights are, as well as the PIP, the posterior inclusion probability, to identify, okay, in this data set for this outcome and this exposure, it seems to be the factors such as the percentage of individuals with a high school education and the percent of older individuals that seem to be driving some of the effect modification. And so we can dig into a better understanding of why might we be seeing these differences across areas. And so just to compare to the first model I talked about, this more flexible model is actually showing us a little bit stronger relationships. So this is a setting where on the horizontal axis, we have the different weeks of gestation. And the different panels are, again, that approximate first quartile, median, and third quartile of these HSF scores. Now what's shown in purple is that fixed index. So when we're using kind of the HSF scores that have been provided by the state, versus now when we're looking at the data-driven ones shown in the dashed green line, and we're identifying that it looks like there is potentially reductions in birth weight associated with PM2.5 exposure for individuals that live in areas with low HSF scores. So this is a really flexible model and tool that we can look at a variety of different contexts in. So just to wrap up with the limited time that I have here, I want to again thank Danielle for her work on this model. This version of it with a single modifier was published last year in Environmetrics. This version with multiple modifiers in the index was published this year in Biostatistics. And we actually also included there an additional analysis looking at modification of health impacts by stress during pregnancy period, and have also a separate publication looking at repeated measures of postnatal parental birth health, postnatal birth parent health outcomes as well. So I want to thank you all for the opportunity to present this. And again, I apologize for the technical issues earlier.
Hi, everyone. I'm Eva Murphy. I'm a postdoc fellow at Wake Forest University, and today I'll be talking about a project I worked on in collaboration with my postdoc mentors, Stacy Hepler and Dave Klein, and their team of subject matter collaborators. This work is on integrating data at multiple spatial scales to estimate the local burden of the opioid pandemic. There you go. So the opioid epidemic is a critical public health problem, particularly in Ohio, where in 2020, Ohio had the 4th highest overdose death rate. Given the severity of this crisis, we would like to understand and quantify the spatial variation of this epidemic so that we can identify areas where this epidemic is worse. However, this comes with some challenges, mainly pertaining to the fact that the opioid epidemic, it's not observable, it's a latent phenomena, as we don't have specific measurement to quantify this epidemic. However, we do have observations for outcomes that relate to the opioid epidemic, such as county level overdose death rates, treatment counts, HCV and HIV infection counts, and zip code level EMS administered naloxone counts. And what we know about these outcomes and epidemics is that they interact synergistically to form a syndemic. So this syndemic view actually gives us a different approach to our problem. And now we are looking to be able to develop a methodology that allows us to model an unobserved latent variable by accounting for the synergistic interaction among measurable outcomes and epidemics in space. One such statistical model that allows us to achieve our goal is the spatial factor model. In these settings, we are assuming that the vector of observed outcomes can be expressed as a linear combination of some latent factors, as shown in the left side of this slide through the matrix equation. Here, F is the vector of the factors, and gamma are the matrix of the coefficients that we call loadings. So the idea again here is that each observed outcome is driven by this latent factor, and even more, this latent factor is shared between the outcomes. A common assumption is that the latent factors follows a multivariate normal distribution, and if we extend this into the spatial setting, then the variance covariance structure has a spatial structure. For example, in the Bayesian settings, we can assume an intrinsic conditional autoregressive or ICAR prior. The factor model as it is, it's not identifiable. Usually some constraint has to be imposed to get unique solutions. One common constraint is it's with respect to the gamma loadings. That is, we assume that it's a lower triangular matrix with ones on the diagonal. One such model was applied by Hepler et al. In their 2019 study, where they used the spatial factor model to model the interaction between death and treatment rates at county level. And their study provides useful information for the broader view of the opioid epidemic. As shown in the diagram, we are able to identify counties where this epidemic is higher relative to the state average, such as the southern areas of Ohio, and also we are able to see where the epidemic is below the state rate, such as, for example, in the northwest counties of the Ohio. However, what this study fails to account for is the within county variation. And this becomes relevant when we want to address the opioid epidemic, particularly in urban areas which have denser and more distinct neighborhoods. To achieve this goal, then, besides using county level data in our study, we need to use data measured at more granular spatial units, such as zip code. In that way, combining county level data with zip code level data, we should be able to provide a more detailed picture, helping to capture this within county variation and better understand the opioid epidemic. So to achieve this step and this goal, we will need to extend the spatial factor analysis to integrate data from non-nested, spatially misaligned area units. And originally, such a model was proposed by Nery et al. In 2019. And the idea here is to take the larger spatial units, such as county level data in our case, and intersect it with the smaller spatial units, such as zip code level data in our case, and conduct the analysis at the intersection unit that we call atoms. Now, I will note here that, as you can see in the graph on this slide, that some of the zip codes are totally included in the county, and if all of them would be like that, then we would have a nested spatially misaligned areal problem, which is very similar to the application presented by Nery et al. However, as you can see, we do have some zip codes that are larger, which then they split between different counties. So that's what makes our problem different. This means that we have a non-nested spatially misaligned areal unit. Nevertheless, so the idea here then is to define our factor at this new smaller unit called atom, and then link this factor to the county and zip code observation using weights. Now, some careful consideration is to be done here. When we define the weights, we use population counts, and population counts that comes from census, the Census Bureau website, and linking or constructing these population weights to link the atom to county is a straightforward work, as we do have county level population data. However, we do not have zip code level data. So before we are able to link the atom level factor to the zip code observations, we need to transform the zip code to a spatial aerial unit that we have data, population data for, and that spatial unit is what we call the zip code tabulation area, or just ZICTAS. And this matching, so this means that we will have to match the zip codes to the ZICTAS so that we can get the population for the ZICTAS and use them in computing the weights we need for our modeling problem. So once we pass through this first hoop, we define our method using the following governing equations. For each settings, county level or ZICTA level, we assume that the observation follow a Poisson distribution, and we use the factor analysis to model the log relative risk of this Poisson distribution labeled by lambda. So that's the second equation on this side, where lambda, we see that it's governed by only one factor labeled by eta. S of n is S sub n is the atom, and W represent the weights that link our factor to the county observations and to the ZICTA observations, respectively. So in the case of county level, this W represents the proportion of county J's population in atom n, and for the ZICTA level, W represents the population of ZICTA K in atom n. We model the spatial variation using, as I said before, the intrinsic conditional autoregressive prior. We impose that prior on the factor. So we estimate our model under the Bayesian modeling framework. And I show the mean of the posterior estimates for the loadings in the table to the left and of the factor in the spatial map to the right. So the factor model, as I said before, had to be identified by constraining that the first loading to be 1. Everything, all the other 4 loadings were freely estimated, and what we observe is that naloxone got the highest loadings, suggesting that the factor is more correlated with this observation, which is to be expected as naloxone is observed at the smaller area, which relates to the atom better. Our factor looks very similar to Hepler et al.'s 2019 study. Broadly looking at it, we do see that the southern counties in the southern region have higher factor values compared to the ones in the northwestern region, but we are able to do an additional step, and that is zoom into a county. And to show an example of what it means to zoom in a county, I'm using Franklin County. Franklin County is home of Columbus and New Albany. These are 2 neighborhoods that are away from each other, and if we would use only county level observations to estimate our factor, as we can see in the graph to the left, this factor would be will have one value for the entire county, a value that is above the state average. However, looking at the naloxone rates in the middle, we see that distributions are not equal, are not the same in the entire county. We do have some variation, like Columbus has higher distributions compared to New Albany. And putting this together, then we can conclude that while county level data provides a broad overview, granular data actually helps us zoom in the county and accurately identify and address specific areas of concern. And we do see that in the graph to the left, where we have our new factor. Now, this poses a question then, why should we not just use the granular data as our only observation, since we are able to, that's the one that drives the within variation information? Well, the short answer for that is because we do have some what we call urban bias. Counties that are more urban tend to be closer to the hospitals, and emergency services get to the areas of problems a little bit quicker. To specifically show you specifically visualize this, I'm using Jefferson County, which is more like a rural county. And we estimate the factor estimates higher values within this county, as we can see in the left graph. However, naloxone, as shown in the middle graph, it's has lower values compared to the state average. So if we would ignore the county level data in this case, as shown in the right picture, we would think that everything is fine in this county. However, we do see that death rates, treatment rates, HIV and HIV together correlate to give us a higher factor, which our factor, the new factor, estimated atom level, is able to account for that. So bottom line is that relying solely on granular data, such as zip code level data for this county, can miss important insights from other opioid-related outcomes, specifically in non-urban areas. And I will wrap up my presentation with a few notes about the limitation. We are estimating our atom at our factor at atom level, and we have about very close to 2,000 atoms, which it's a lot of a large data set, and it took us about 7 days to complete the estimation procedure. So there is a computational cost that comes with this problem. Also, our data is surveillance data, so we do have bias that comes with reporting that data. But because we are looking at the interaction within different data set, we see that these outcomes help to give us a better picture and make this bias be smaller. And finally, we have this work published in Biostats, and that's where the top journal, the top work is on, and then the other two I mentioned, Hepler et al.'s 2019 study and Nethery's study are the other two works. So if you have any questions, I'll take them. Otherwise, you can email me at my email address. Thank you.
I think we're at time. So thank you all the speakers and then attendees being in our presentation. And we hope you enjoyed this discussion and encourage you to explore the remaining sessions of the conference. Thank you so much.